So the last species we need to consider is the intermediate form. If we had a 0.1 molar solution of HA, what would be the pH of that? Now here we have, again, two equations we need to worry about. HA can act as a proton donor, as an acid, and create a proton plus A minus. All right, and that's given by Ka2, which is 10 to the negative 9.868, like we've seen before. And then we also have the base, which is, same species can act as a base. So it can form the protonated form H2A plus hydroxide, and that'll be governed by Kb2, which is equal to Kw over Ka1, which is 1.0 times 10 to the negative 14 divided by 10 to the negative 2.344. What we can see here, if we went through both these calculations, is that these are both small K values. So HA is a pretty weak acid, but it's also a pretty weak base. And so this is a species that we describe as amphiprotic, meaning that can act as either an acid or a base. And the question is, which of these matters more? And the answer is, it's hard to say. So our calculation is a little bit more complicated than for either the fully protonated or fully deprotonated forms. We have to worry about both of these equilibria. We can't ignore one of them. So what we have to do is go through a more systematic treatment of equilibrium here. This is what's covered in the end of chapter 8 that we didn't go over, but we'll just go through it together, even though we haven't gone through the overall formal treatment of this. Okay, so when we have multiple equations, multiple unknowns, we have a few, we need to come up with multiple equations to find those multiple unknowns. So the first thing we're going to do is look at the charge balance, which means we need to consider all the positive species. So that'll be H plus and H2A plus. And one thing I'll mention is that the approach that we take here is specific, right? We're considering alanine specifically. With other acids and bases, the charges may be a little different on the protonated and deprotonated species, but the results will work regardless of whether we have the same charges as we do for alanine. Okay, so our negative ions are going to be A minus and hydroxide. Right, so all of the positive and negative ions have to have equal concentrations when we add them together. Or we can rearrange this and write this as H2A plus minus A minus plus H plus minus hydroxide equals 0. Okay, so now that we have this relationship, what we're trying to do is get everything in terms of a few variables. So let's substitute. We want to eliminate some of these. Let's substitute concentration of H2A plus and A minus. We want to get everything in terms of K values. We'll substitute those from their K expressions. Okay, and what those expressions are going to be, so H2A plus shows up in Ka1. So we can write that concentration of H2A plus, we rearrange the Ka1 expression. We'll have HA and H plus divided by Ka1. So we just took Ka1 and swapped and rearranged it to solve for H2A plus. And we can do the same thing for A minus with Ka2. We're going to express everything in terms of Ka's here. Right, Ka2 is equal to HA over H plus. And we're also going to get hydroxide out of there. We want everything in terms of H pluses as much as possible. So, and HA. So concentration of hydroxide is Kw over H plus. All right, so making those three substitutions into the equation that we have for the charge balance, we get, so again, this equation up here, making the substitutions that we have there, we have HA times H plus divided by Ka1 minus Ka2 times HA divided by H plus H plus minus Kw over H plus equals 0. All right, so again, these substitutions are just direct here. All right, so what we want to do here is solve for H plus. That's what we're after. We're after the pH. And this is taking into account both equilibria simultaneously. All right, so to solve for H plus, let's multiply by H plus. That gets H plus out of the denominators in a couple of these fractions. So we end up with concentration of HA times H plus squared over Ka1 minus Ka2 times HA. The H plus cancels there. Plus concentration of H plus squared minus Kw equals 0. All right, and now we want to reorganize this to get H plus by itself. So all these two terms here don't have H plus. We'll move them over to the right side of the equation, and we'll collect the H plus terms on the left-hand side that both have H plus squared. All right, so we'll just keep going through this algebra here. We're almost done, by the way. Concentration of H plus squared times concentration of HA over Ka1 minus 1. Oh, sorry, plus 1. That's a plus sign there. Is equal to Ka2 times concentration of HA plus Kw. All right, and then we can divide by this expression over here. Over here. And we have an expression that gives us concentration of H plus squared is equal to Ka2 times concentration of HA plus Kw divided by concentration of HA over Ka1 plus 1. Then we can take the square root of this whole expression. And there we go. We've solved it. This is the expression that we get. We can rearrange this a little bit. Our final version of this, I'll write below, is the concentration of H plus is equal to the square root. We can combine some of these fractions on the bottom here. Right, we have something over Ka1. And, we'll multiply the bottom by Ka1, bottom and top by Ka1, which lets us cancel some things. So that gives us Ka1, Ka2, concentration of HA plus Ka1 times Kw, because we multiplied both top and bottom by Ka1, divided by concentration of HA plus Ka1. And now we don't have multiple levels of fractions. All right, so up to this point, we've had no approximations. The only approximation we've made is that we're ignoring activity coefficients, which we're going to do for the rest of this chapter too. But we get an expression here. Now, in the next video, we're going to look at how we can simplify this. You can use this expression as is to find concentration of H plus and find the pH, but there's some a little bit more, one pretty simple approximation we can make, and then we can simplify this even further that will work for the majority of cases.